Okay. So what we're going to do now, we're going to talk about the Linux file systems. My name is Ron Munitz. I lead a consulting group called the PSCG. I lead a couple of startups, and I'm involved in several things. I work for the Linux Foundation as contractor, and I do all kinds of things that are embedded. For those of us who are first time here and ask me to introduce myself, and we can talk about me at another time. Here we gather to talk business, right? So the business we're going to attend is talking about file systems. So in this module, we're going to talk about basically how Linux prepares the ground for the populating of the first file system. That is how actually we're going to execute Init, the Init executable that we already covered in the previous meetups and in the following videos that I put in on the YouTube channel, which is this one, Ron Munitz. Okay, so here we have several videos that you can look at. Some of them are from Embedded Israel, some of them are addendums, all right? And there is like a playlist, I suppose, with things like that, okay? And we're going to cover, in order to understand like how we actually start some things, we're going to cover some of the data structures and concepts that every file system should be aware of. Now, these concepts tend to be quite complex, okay? And addressing them properly, giving them the respect they deserve, is going to take many hours, maybe many days. It always depends on what you want to concentrate on. And I do this kind of things on my training. So if you really need something for work, you can reach out for that. But now we're going to start small, and we're probably going to scatter this across several meetings. Why am I saying probably? Because it's up to your feedback. If you guys and girls are interested, then I'm going to do what you want. And if I see there is no interest, I'm not going to waste my time talking about those things. Fair enough? Okay. So in the previous talks, we were covering the kernel initializations. We were talking about it in several architectures, both about x86 and ARM, from the very low level and initial initialization phases. And our objective was essentially to go to the place where, if I'm on the kernel tree, then we run the common function that is called start kernel, that each and every one of the ARC code, that is architecture dependent code, it is very early code by ARM, by MIPS, by PowerPC, by x86, is going to call in order to have this common code, all right? Now, this common code is going, as we mentioned, to sometimes do jumps back and forth between the common code that is C, that is generic, and yada, yada, and whatever we have in the architecture dependent code. So it's not going to be, of course, only like drivers, but it's also going to be drivers. But rather, we're going to also have low-level routines like, okay, if I need to allocate memory, then I need to enable the memory subsystem. And each memory of every architecture behaves in a different way, right? Like paging in x86 is not like paging in ARM, for example. The concepts are, of course, identical, but implementation is very specific, right? It's a different assembly language, it's different architecture, it's different everything. So here, what we're going to cover is some of the steps that lead us to executing one of these guys, hopefully, spinit, etcinit, binit, or just /init, okay, that are going to be listed and controlled by several boot commands that maybe I'll cover a little bit later. We already covered some of them in the previous meetings, and this is not the intention to go and teach everything. We are time limited, all right? Now, we already reasoned that start kernel is going to be called by an external function. Tons of initializations are going to happen. Some of them that are relevant for our discussions today are VFS, that is Virtual File System Caches initialization. it's going to happen twice. One time after enabling allocation of some pages, and later after enabling the entire memory subsystem. We will have init function, which is going to be somewhere here. Let's see. Yeah, so we're going to have a memory initialization function, okay? And after that, we actually have like the entire like phase of initialization of all kind of things. And later on, we're going to have another phase of like VFS cache anything, okay? So I'm going to be covering these things. You can see while I'm going over it that we have, for example, setting up, those of you who care about security, of the credentials. Like if you want to patch something and say, hey, every user is like user ID 0, then this is what you patch. Initialization of like fork and stuff like that, of the UTS namespace and so on and so forth, and a later phase of VFS caches in it. So these are two important concepts that I'm going to be covering today, where our goal is eventually to do the rest of the initialization that might or might not be architecture specific. And then, as you remember from previous times, spawning the kernel init thread, okay, which is going to do all kind of things like freeing memory. I'm not going to repeat that. And do this running off the init command, okay? Now you have here all kind of concepts like RAM disk execute command, and so on. This depends on kernel parameters, right? So we can see, and I always, you know how I do. Always when I present something, by the way, I show some concepts. But so you can see that here this is an initialization, an implementation of like a setup function, right? So all over the kernel, you'll have things like this, __ setup equals some string and a function handler. So this means that if you give the kernel command line of rdinit equals whatever is over there, then the function receives this whatever is over there parameter. And here we're going to set like this RAM disk execute command. Okay, so this is like how things are. So this is not the critical thing over here, but this is what we're going to be covering. So recap, kernel init is going to call run init process that in turn is going to actually start do something like fork and exec, but it's not going to fork because it already started the kernel thread. All right, so it's just going to change its memory map and do a magic that will cause it to be like a user space process. That is, it's not going to be in the memory address space of the kernel. So this guy later on does all kind of forks, right? And this is why you can see this nice tree in PS3 that you have like all these guys. All right, great. So the overall objective is to refer to this init process. It can be /sbin init, it can be a lot of other things that is on some device. It could be a physical device, it could be a memory device, it could be a remote device. If you're able to somehow go ahead and communicate it via some protocol, for example, via NFS protocol over some medium, for example, over Ethernet, or you name it, okay? And if it is able to go ahead and actually use this guy and parse it, then it can execute its content with something that is called bin format. So we covered it a little bit in one of the previous meetings, but just to keep you in the loop, sorry. And basically, the bin format is going to be, one of its example will be, for example, bin format elf, okay? Another one can be bin format script. This is the easier to demonstrate. So the idea is like this. If you have like a file that starts with a shebang, right? For example, bin sh, and then it does all kind of things, then how come you can run this file externally? So the idea is that the kernel itself, and this is something that a lot of people are like, wow, what's going on, is going to interpret some things in the file. Sometimes it will interpret the magic, for example, 7f elf, right? And other times it's going to say, hey, this is the text. It starts with the shebang. I'm going to go ahead and parse like the string itself. And then it's going to say, all right, so I know how to do it. So what does I know how to do it? In the case of the string, it's going to say, all right, this is the interpreter. I'm going to load the interpreter itself. And then it's going to actually use another bin format of ELF. I can cover it more. We did some talks about the ELF file format, executable and linkable file format. We're not going to repeat it here. So just for the example, for the sake of completeness, bin format script indeed has this thing that I noticed. It has a buffer. It's going to look at this and at this. I'm going super quick, so if you don't understand, it's okay. And it's going like to parse the file and then say, okay, like I'm going to read whatever is going up and whatever is going to be after there. And once I parse it, I'm actually going to go ahead, see what is the name of the interpreter, for example, /bin/bash, and then go and call openexec, for example. Okay. So we have here a way to load these things. And those of you who already started playing or are very experienced with the kernel can see how it goes by applying the methods that I taught in the previous meetings, that you have to go like with a debugger and teach yourself, essentially. This is an important part of it. Okay. So the idea is that we have a backend device and we have a way to execute a file. And we just need to somehow get the file from this device. And when we get the file from this device, we want to actually go ahead and create all the infrastructure, all the ecosystem to go ahead and bind what it means, a file name, and how it actually is connected to whatever is on the device. So in order to do that, we need a concept called file systems, okay? And we, of course, in order to get to the device itself, we need device drivers that understand how the hardware works, writes whatever is needed to wherever is needed, and so on. And I thought I put it on silent, so my apologies. For some reason, phone is still calling. Okay, sorry. So, so we're going to need to, of course, communicate with hardware. And the other things we're going to need is to understand how to actually, what a file path is and how it gets to whatever. And for that, we need a concept of file system. Now, when we talk about a file system, we talk about, okay, one particular file system can be mounted into several places. So if you just do like the command mount, you're going to see that we have, for example, in this example, we have like a type C group that never mind where it is right now. We have a real device, dev SDA5. It's mounted on / this is my root file system, and its type is ext4. Okay, we have virtual file systems, and so on and so forth. And the file system that we support are going to be over proc file systems. So a lot of times you see, I'm going to put it here so it will be a bit easier. A lot of time we see the word no dev, and take a second to look at it, like sysfs, cgroup, okay, encryptfs, fuse control, bin format misc. These things, bdev, ramfs, rootfs, these mean that there is no real backing device, that these are going to be like in memory, okay? Other times, we're actually going to have these things that are file systems that are implemented. So sometimes you implement them on a device, which is a block device, okay? So if you have like a hard drive or a loopback device, and you want to go ahead and represent its information in some particular way, then you're going to mount it in this way. And in this case, you do have a device, okay? So all these fellows here need to introduce themselves somehow to the kernel. This is by registering a file system. And registering a file system and just having the names is not enough. We need to support a lot of other things, right? So the other thing that we're going to need to support is a way to actually do something with this file system and mount them into some place and do all kind of other things that I'm going to talk about, of course, okay? So in general, once upon a time, we had a single namespace billions of years ago in the 2.4 kernel era. And later on, in the first namespace, you guys who don't do too much kernel programming know it as maybe as containers, Docker, LXC, whatever. But the first namespace of it was the mount namespace. So ideally and generally, you can have a process split itself and start like a new namespace, and then it has like a new mount hierarchy. So like the mount command over it will show other things. I think somebody tried to join, so let's maybe give them a shot. Okay. All right. So we're going to talk about this kind of thing. So our objective is to do the following things: create an initial namespace, create a file system concept in the kernel, let the kernel know the file system, mount it into a particular mount namespace. There is always at least one mount namespace, for example, the init namespace, okay? And I will give maybe a very, very, very minor introduction to what namespaces are in terms of where they sit, where the proxy of the namespaces sits, like in the task tract, okay? We want to find, once we have like the file system, we want to find the file init over it, okay? And we are going to go ahead and after it execute it, okay? So these things are identical no matter what type of file system I have, okay? If I have like an ext4, or I have some NFS, or I have some ButterFS, or I have some TempFS, then I want to do essentially the exact same things in order to find this init, okay? So there needs to be a generic way and an efficient way. When I say efficient, I mean that there are some operations that happen all the time, and it would be smarter to not go ahead and fetch them from disk all the time, or recalculate very long string names, or compare very long string names. So we're going to have a lot of caches and hash tables, okay? So when we have like in the file that I showed you, like in init main, like a to init VFS cache and stuff like that, this is one of the reasons for that. And of course, one of the ideas is also to support a programming interface. So when you do read, write, seek, and so on, then basically, okay, now I admit it. New people who come to the meeting, register before, okay? We cannot afford to admit everybody all the time because we're busy teaching, right? So basically, sorry about the interruption. Basically, we also want to be able to do something like to get into kernel space, right? To do system calls, to do all kinds of things like that. So the idea is that we want to implement this in a very generic way. And this is one of the things that the VFS, the virtual file system, does. Okay? Sorry, there were some kids making some noise here. All right. So, so this is another thing that the file system needs to be doing. Okay. So here it goes. So some of the important things about our walkthrough is that there are many initialization patterns according to the way that we start the kernel. So I'm not going to cover all of them. And today, I don't even know if I'm going to cover one of them or two of them, but I'm going to go and like if we do it several times, I'm going to go and actually show and demonstrate these things, okay? So the overall picture is like this. There is an early initialization phase. Excuse me 1 second. Okay, so there is going to be an early initialization phase, okay? And this early initialization phase, as I mentioned earlier in init main.c, sorry, is going to actually be here in VFS caches init early, okay? Before we initialize like the memory in fully-fledged. So what we have here is going to do the following things. Pay attention. We have here an hash table. I'm not going to go too much into it, but I'm going to give like the the pattern of use. Hash table in order to do some lookups. And we have here two things that are interesting, and I will explain what they are very soon. One that is called dcache, that it's for caching the entries. And the other one is for inodes. Now, the init early pattern is actually added here, all kind of print, so that if we do walkthrough, then you have color and stuff like that. The idea of the init early is that at these phases, I have an opportunity to allocate large contiguous block. Okay? So for example, if I go back to the dcache init, we can see that we have the entry hash table, and we have an alloc large system hash that has the hash early modifier. I'm not getting into the API one-on-one, okay? But I just want to show you that before we have two such functions for a dcache init and a early and a dcache init. And in the first one, we have hash early, and in the second one, we do not have hash early. What this means, and we have a very similar construct on the other one. Sorry about that. I really ask you guys to not join after the meeting starts, especially people who did not register, because it really interrupts us, okay? I don't want to let anybody out, but I can't afford to let everybody in. So the inode one is going to look pretty much the same. So we're going to have, again, alloc large system and then hash early, okay? And in the inode, we have another type of initialization that we'll see later. That is, of course, the alloc large system hash without the hash early. And we have Checkm8 cache create. That those of you who have absolutely no idea what I'm talking about, then this is one of the things that like Checkm8 does. It uses a cache, but the cache systems, when we talk about early, does not exist yet. So if I go to this alloc hash, I can see that it's going to look at the flag. And when I look at the flag itself, then it's going to go ahead, and if the flag is as like the flag early, it's going to allocate something that is called memblock. Okay? Now, those of you who have done Linux for a while might have heard of bootrom that enable us to allocate contiguously large memory, because you don't have necessarily all the opportunity that you want to do that. So basically, this is what those big caches that work with the hash early method does. They allocate a hash table, they allocate memory for a hash table in a big contiguous memory. Okay? So I'm not going to look at it with you right now, but this is what happens on the early phases. And on the later phases, we're going to be calling more advanced caches like Checkm8 caches. Okay? So these are two things that we're going to do, two phases of initialization, because there are two types of like memories that are available for us. All right? Now, we're going to have several types of caches for several entities that make the file system concept and make the VFS, the virtual file system concept, okay? So there are quite a few of them. And at the end of the day, a file system will be registered with registered file system. Once we allocate everything automatically, assign the right thing to the right places, and set it in a file system context and a file system type that would be registered. All right? Now, the objective of this talk is to give overview, so it's okay if like you understand 30% of what I'm saying now. As I said in the beginning of our meetups, the idea is to help you to teach yourself. Okay? So this one will be a little shorter than the other ones. So I will give concepts, and perhaps if it interests you, I will elaborate on them the next time. Okay, fair enough? Good. So let's go back to what we've seen. So this is the init, early init initialization. That's all it does, initializes some caches. And later on, you can see a call to VFS caches init. All right? But it's later on, there it goes. Now, pay attention to that. There are all kinds of caches in the system. There are all kinds of process caches, parallelized caches. There are all kinds of page caches, okay? And there are caches that have to do with the file system elements themselves. So let's go ahead and have a look at them. But before, let's see the APIs that are called. So we have dcache init to initialize something called a dcache. We have inode init. We have files init. Files max files, I'll talk about it later. And later on, we have a function that does mount init that actually is going to take care of, along other things, making sure that we have our initial root file system where we're going to have like the /init or /spin init placed. Then we have allocation of additional things. And this is very, very, very interesting. Why it's very interesting, although I'm not going to talk over them, because we have here block device cache init and char device init. Now, as you guys know, everything in Linux is a file, right? So we have, for example, this virtual console that is a character device, right? And we have, for example, this body here, SDA, which is a block device. Now, I can do operations over it. Open, read, I/O control, okay? I can do the same over, for example, sockets. I can do the same over pipes, and so on. So the idea is that when I do the VFS caches in it, then this big entity is there was a question, why need for contiguous memory? So the answer is very simple. And if you have a question, please jump on, all right? Because I will not see it otherwise. Because the moment you go and use the system for a while, okay, then you would sooner or later have fragmentation. Now, I can talk about memory allocation later. Those of you who are very familiar with it, the way to defrag the memory is using the body system. But if you want to, for example, allocate, I don't know, like 100 megabytes of like contiguous memory, then good luck doing it after the system booted and did all kind of things, okay? It's not that easy. If you have huge pages and you reserve huge pages, it's easier, but never mind, we're not talking about it now, okay? So fragmentation of memory is like basics of memory allocation, and this is the reason why you'd want it, all right? So back to our walkthrough. So what I reasoned about is that we have all kind of like file system related entities, and there is a VFS that implements all kind of APIs for the programmer, for the user space user. So block devices and character devices are part of the users over there, okay? So speaking of the caches, which we're going to talk about right now, we have here, as I mentioned, something called dcache, something called inode, and something called files, okay? Now, another thing that we have here is names cache p. That's the name of the data structure, okay? Which is created by using Checkm8 cache create user copy. It has a name, names cache, and it has a size of an object, okay? And it also has all kind of allocation stuff. So, for example, I want the objects in this cache to be hardware cache line aligned. And if I can't allocate this cache, then the kernel will panic, okay? So we have here a way to create a cache, which, by the way, those of you who do security research and know like how malloc on the user space works, then concepts are pretty much similar, okay? We manage some way of caching, and like in malloc, we use like the heap, the forest, all kind of things like that. And usually when we don't want to like reallocate and do some things like that, we're going to cache something. So these are like the concepts, okay? So back to our actors. I'm sorry about the jumping back and forth. You'll have it recorded, so it will help you when you see it again. So we're going to have all kind of caches that I'm going to talk about next. And we're going to have a lot of structures that I'm going to cover some of them. So for file system type, I will sooner or later register it over the kernel, okay? I can go over slides. I prefer to always show code. So who are the players and who are the caches? So the first one is going to be inode. Inode is going to be a metadata on the file that we have on the device itself. So if you have things like permission, like a file size, like number of links, okay, like hard links, like extended attributes, like all kind of things like that, that your block device, for example, will have, then this is represented by inode. So essentially, everything in every file system has an inode, and you can be convinced. For example, if you go, I don't know, like to dev just for fun, and I'm going to pick something at random, and I'm going to do stack to loop 8, then it's going to say, hey, size 0, block 0. Okay, it's completely virtual, makes sense. Block special file, great. Device, main or major minor, inode 5 or 3. Okay, and if I'm going to take something else at random, for example, 0, dev 0, that I'm just going to read zeros from that, then this has like the inode 8. Okay, so we have all kind of these things. Fair enough? Good. The entry is metadata on path. So there is a challenge here. Inode represents something on the disk itself, okay? Now, if I want to give like a path, for example, /dev/loop6, then I need to somehow bind it to the inode. It could be virtual. It could be like on an on like a physical disk device or something like that. So struct D entry actually takes care of that. Struct file that you would recognize from like your system calls, okay? Let's just give you like a quick recap of those do kernel development. If I now go to FS and do VFS, read write, just for fun, okay? We change it to KC, okay. I have VFS write, and the name was changed, okay, to kernel write or KE write and all these kind of things. There used to be like, there's supposed to be like syscall define and so on. So this is the implementation like of the system call essentially. So one of the things that it received is a struct file, okay? It receives a buffer. This is the buffer that I will write. Like this is the corresponding of, if I do man write, then we have this API, right? File descriptor, which is an integer, which is represents something on a table, okay? And that corresponds to the files on the left-hand side. Buffer is the buffer that I'm going to write, user space buffer, and count is like the size, okay? So essentially, this kernel write is going to do this kind of things. It also receives like the current position, like the offset, or if I do like elseek and so on. And I'm going to work on a data structure that is called file that we'll see a little bit later, some of the things that it has. So what is file? File represents the file concept in memory of a process, okay? You will see that there are all kinds of structs in the task struct that represent that. So we're not going to take care of it right now, but this is the struct file. Those of you already know, all right? So, so all of these are going to be used in all possible file system implementations that you might know, like what we printed when I printed /proc/file systems, like ext4, ext2, NFS, Sieves for Windows, Fuse, which if anybody's interested, I'm going to give another talk about it. It's file system in user space. Very, very, very useful. TempFS, RAMFS, ROMFS that we're going to see a little bit today also. SysFS, DebugFS, ProcFS that we talked about, and we'll talk more. So all of them, all of these players are used in this file system. And the idea is to represent something in some device. So even if there is no real device, then I can go ahead and fake it. So some of the initialization that we're going to do is also to go ahead and create a device that does not necessarily exist. So I mentioned caches several times. So we need to cache these elements, but we could live without them. Why do we need them? Because this way things are just going to be faster, okay? So why do we need them? So what happens if you do, like if you search something using find, or if you print something for the first time or load something for the first time and then do it again? What's going to happen then? Then the second time that you do anything like with a file, then probably it's going to be much, 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 but much faster, okay? Anybody answer that? No. It's going to be much faster. So this is because of the use of caches. All right. Now there are other reasons to use caches for memory management. When you do kmalloc, then it uses kmem cache under the hood, and it has all kinds of reasons to do that, for doing overcommitting, for very small locations that are like much less than a page, which is usually 1K, and so on. Okay. So who are the caches? So before, when I showed you like some of the code, I said it, and those who know me know that I repeat important things millions of times. So the inode cache will cache access to inodes. Otherwise, we'll need to get them from the disks. The entry is going to make lookup of the entry object that I did not mention exactly. I said that they bind between like a path name and an inode. So they're going to do their lookup much faster. Page caches are going to actually have like the page contents, but cached. And memblock, kmem caches are generic mechanism. Memblock, earlier it was called bootmem, before 4.20. Then it's going to be to have like contiguous memory that is going to that you can allocate only very early, like in the boot process. And kmem cache is the mechanism, for example, behind malloc. Okay. So now we're back in business. Kernel initialization flow. When we start, I already told you that we have like the VFS caches in it early. So it's done before the Init, and after we have like the zone list to actually see what is the initial fragmentation. We're going to allocate the entry cache. In my reference system, it was this amount of pages, and inode cache. In my system, this amount of pages. Okay. And we're going to have the entry saved, as I showed earlier, of the entry hash table and inode hash table to access them. Now, the hash tables themselves, if it interests anybody, please let me know, and I'll give like some data structure, some kernel data structure talk. Then the idea is to use, like a mapping, and the hash constructs in the Linux kernel are going to do two layers. Like one of them is going to do some hash function, and the second one is always going to be like a hashed list, which is going to be a list of the collisions. So you always have these concepts. When you look at the code, then this is why you have all like these weird or not so weird data structures. Okay. VFS caches in it is what we're going to focus on next. So as I said, it creates the name cache. Okay. Which essentially is just going to be a slab, like a kmem cache and so on. And you can allocate from and deallocate from with this function, get name and put name. The name is going to be a string of a path. Okay. The cache init, inode init, and files init are going to take care of the players that I mentioned earlier. And mount init is going to set up several file systems. Okay, so we're going to cover it today and maybe stop there. vdev cache init, chardev init creates some fake devices, and so it initializes some of the file systems for like block and for character device. Now there are reasons to do that I'm going to explain later on. Okay, so here I have like a quick reference, because I'm going to jump over it, of which function happens where and takes care of what. So when you see this video, or maybe if I publish like the presentation, you'll be able to go ahead and explore these things. So here we have the object types, except for car and for this file except for this car, which is like a string. Then all of these are struct and the name of whatever is listed. For example, struct inode. Okay. And the functions here are the functions that I'm going to be calling. Okay. So these are here, dcache init, inode init, and so on. Okay. So usage says, okay, what I'm going to be initializing. And the data structure name is like a data structure that is like used over the kernel. So some interesting things for those who like don't care about any of this at all. The maximum number of open files is going to be listed by, it's going to be set by this function, but the file start by files max files in it. Okay. Go back to business. Sorry.
One of those parameters that you've shown us, are they tunable? I assume they are tunable.
Yeah, some of them are. Yeah. So the file one is tunable by syscontrol. Okay.
Okay.
There was a typo, but it doesn't matter. Okay. So this, I'll go back to where I was, and we're here. Okay. So Checkm8 cache creates a cache. Okay. Dcache init. You're going to see the same patterns for all of them. Going to go ahead, create a Checkm8 cache, set a hash table, this time without the early one, and these two are going to be used, these variables. Okay, so that's the first one. Second one, inode init, it's going to be very, very, very similar. So we have, for those of you who have absolutely no idea what these caches are and what I showed earlier, it's the exact same code written in another way. Okay, so we have a Checkm8 cache, we call it inode cache. And by the way, you can go ahead and see with all kind of like slab top and things like that. For example, you're going to see name of all kind of caches here. Okay, so let's find the word inode. Yeah, so for example, inode cache is going to have like objects or caches of objects of a particular file and so on and so forth. Okay, so these are things that are known. Okay, there's no like secret in anything. Files init is going to initialize something else. We have here something called file table, and it's going to be used by the process. I will elaborate it on the next talk, perhaps. Okay, so we have here a filled cache that is creating the exact same thing, but on this time, it actually opens struct file. Okay, so struct file is going to be under fs.h. It will be actually faster for me to just open it. So look at some of the things that struct file has. It has path and inode, and it has file operation. So this is when you call like system control, when you call IO control, or when you call read, write, open, and so on, you actually see this thing. Okay, path is, I actually have like a print of these things, and let's go ahead and just show them because I knew it would be like a waste of time to do that. So path has something called the entry that I'm going to cover later, and a VFS mount that I'm definitely going to cover later. Okay, and I know there's a lot of things. If you can see, if I can like make it a little bit bigger, you would see that we have like the mode, okay, and that we have a user ID and a group ID, and we have modify time, and so on and so forth. Okay, so these data structures are things that are like going to be stored for each process in its task struct, and are dedicated struct that encapsulate it with it. Okay, and max file init, one of the things that it does, Eyal, is like to set like one of the tunables that is like max files here. Okay, so it's going to be initialized as a dependency of how much memory you have. Okay, you'll see these calculations also for calculating the maximum number of processes and so on. And that's how it's going to be initialized. Okay, so the next thing here, mount init. Now mount init is going to be interesting. First of all, it's going to once again create some caches and hash tables. Okay, why? Because we want to quickly access the mount points and to access the mounts. What is a mount? Good question. Now there are several APIs here. Kernfs init, sysfs init, that, as you can imagine, initializes sysfs, and it does it by calling kernfs create root, forget about the parameters, and register file system. So we have a file system type that is called here sysfs type, and it has a name, something that is called a context, file system context, that tells a lot of things about the file system itself. Fs flags, which is, it represents some of the flags that you would give, for example, in the mount command. and kill superblock, which is what is going to do, what is going to run when you unmount something. Okay, so we have here kernel-fs create root, and we have register file system, and register file system is going to actually look for this file system to see if it's already been registered, and if not, it's going to add it. This is this find file system, and if not, it's going to add it. Okay, so that's how it's going like to do it. So we have here this sysfs init, which is an example. We have here, I'm not talking about it now, but kobject create and add this fs. We need sysfs to have the concept of kobject. So this essentially says that we're going to have the fs hierarchy under sys. Okay, so this is what this line does. All right, kobject create and add, and then we're going to call init rootfs and shmem any init, and at the end, we're going to call init mounttree, which is going to take care of like finalizing initialization of init. But we're a long way from there. As I said, this is going to be broken into several parts, and it's going to take a while. So I'm just going to try and at least summarize some of the interesting things now, and we can proceed it later. Okay? So here it goes. So I skipped the kernel-fs init. So if I go to kernel-fs init, I see once again that we create just caches. Okay? Same concept all the time. What we do with them, okay, this is when file system is actually going to be used. Sysfs init, we already had a look at it, right? Now, next interesting things is init rootfs. So I'm going to go to init rootfs that it's under do mount, but you can see that this particular one is not very, very interesting. It's just going to set the ground in the shared memory init function for if we use something called tempfs. Now, what is the reason for this? The reason for this is that in the past, in init rootfs, we actually registered the root file system, and there was an evolving of the file system that we use for memory when you initialize with it. Okay? So let's go back to the slides. I'm going to make things a little bit more organized for you. All right? So our objective is to call these things, particular mount init, which is where we stopped. Now, let's start talking about data structures a little bit. So the concept when I want to do mounting of a file system is like this. We have a D entry of the mount point root, like a path of a mount point root that represents all kinds of things. And I'm going to run a mount command and flags. And this will mount this D entry to a super block. Super block is some sort of a data structure that is on the device itself. And if it doesn't exist on the device itself, then we need to fake it. Okay. And a super block in, like, for example, an ext4 on like a hard drive is going to be stored actually in several places for redundancy because it's a data structure super important. This is where you start from. Okay. So mounting actually introduces the kernel to the concept of a super block, and the user, whether the human or not, can refer to it in some way or another via something that is much easier to manage, like a D entry. So you know struct D entry, for example, if you want to go ahead and look at all the files, do like ls and so on. What happens in mounting? What happens is that we're going to generate something that calls VFS mount that's going to bound these two fellows. So struct VFS mount has struct D entry, has a super block, and has flags. Okay? So back to mount init. We create mount cache, we create the mount cache and the mount point caches. We do kernel-fs init that we saw already. We do sysfs init that we saw already, and also register the file system. We add the kobject, And we have Checkm8 init that I'm going to cover now. It does two important things. It registers a file system called Checkm8 fs type, and it calls Kernel_mount. Kernel_mount, as you can guess, does this mounting magic. Now, Kernel_mount does it internally over the kernel. It's a shared memory file system and does it internally over the kernel. But it does it, okay? So let's so that's what we're going to see like soon enough. But for now, from our current discussion of kernel_fs init and sysfs init and so on, if you understand how to use sysfs init, if you go to it, you can understand very easily how to implement your first in-kernel file system. It's very, very, very easy. Okay? So let's go to mount init and to Checkm8 init. Checkm8 init will register a file system, and it will do a kernel mount. So you will not see it in every possible kernel version. But the reason it was introduced is because of things like doing a pivot root and change root and things like that. Because there are all kinds of limitations and including like a limiting size of like a file system and so on that have been done like on the older default file system that is RAMFS, that in my minimal configuration that I showed in previous meetup is what we were using. Okay. So the thing is that we don't even need this. We can just go ahead and use init and use the init mount tree function because it already knows like the rootfs. I'm not going to show the code. But since all modern systems do use it, let's go ahead and do a walkthrough over it. Then we're going to recap the first part because I want to have another very interesting conversation and we don't talk. And I will continue this, okay? I promise you. But on the next meetup, that maybe we'll do it even like sooner than next month. And we'll recap this one, which is super important, and then we'll take a quick break. Sounds fair? If you guys want to stay more hours, I'm perfectly fine with it. But this time I said, all right, let's do it a bit shorter. So here it goes. So mount init calls Checkm8 init, which is what we're talking about. It allocates inode cache. It's not so interesting. It's going to be exact same thing. We register a file system in the same way the sysfs does. We need to, of course, learn about the file system type. And after it registers it, then it uses the same data structure to call Kernel_mount. Now, Kernel_mount itself is going to call something called VFS Kernel_mount that receives a type that is the type that we give it. SB Kernel_mount means, okay, super block Kernel_mount. It's like a fake super block for the kernel. And the name of it is tempfs. So when you do mount and see, hey, it's tempfs, that's what you see here, okay? After it, it's going to call real mount, which is just container of this data structure in order to say, okay, this is like the namespace that contains this. This is struct mount, sorry, that contains this VFS mount data structure. This is the return. It's a VFS mount that I showed earlier. This is the return from VFS Kernel_mount. And set on the corresponding mount a namespace that it's internal, that it's in the kernel. Okay? Later on, what we're going to have is init rootfs. That is not important. We already covered it. And init mount tree. So back to VFS Kernel_mount. Here it introduces the concept of file system context. Okay? That is going to be allocated and created here. Then it's going to get the root of this, and it's going to create the mount point itself and create a VFS mount member. That's what we're going to return from these guys. FS context looks as follows. We're not going to cover it too much, but it has a D entry for the super block. Okay. It has a user namespace and a network namespace and credentials. All right. And the file system type. And the kernel parses this, and according to it, it knows actually how to do the mounting itself. All right. So it's very important. Last thing is init mount tree that is also going to call VFS Kernel_mount this time on another type of file system, rootfs type. And then it's going to allocate the init mount namespace, and you can go ahead and look at it. So if we looked at the code of init mount tree, then we're going to see that we have struct vfs mount, which is the return of this fellow here. Okay. We allocate mount namespace for the init user namespace. And then we set all kind of parameters, add it to the list of namespaces, okay? And set in the init task proxy, we set the relevant mount namespace. What is this proxy? So those of you who heard about Docker, heard about containers and stuff like that, take 10 seconds to look at these names, okay? So essentially, if you have like a very isolated Docker instance, then it isolates everything, okay? So it does it by creating namespaces of the following of these kinds for the corresponding process. And in our case, it would be the init, it's going to be the init task, okay? Because this is how like we start with the init task, which is speed1. Now, what is this file system that we talk about? It has all kind of things. And one of them we mentioned, kill superblock, okay? The entry, which is where we mount. And this is the return of a mount function. So when you call mount, this is going to be a callback that is going to be called, okay? And how do we set it up according to the context and so on and so forth. So there are quite a lot of things over here. And when we register a file system, we just add it. We don't do anything about this activity. We just add it and that's it, okay? So we're going to recap what we've done like for now. I'm not going to show too many examples because we will go to the next talk. As I promised, this takes time to dive into, okay? Just one more thing on how we connect to this and how we connect like the files in the process itself. So if we go and look at tasks, task struct, and I'm sorry if it's been overwhelming. Those who understand some of the concept and been in the previous talks, I'm sure that they managed to follow. And those who didn't, I'm sure they didn't understand anything. That's life. No, come to the lectures, learn, practice, and you'll know more. So task struct, as we of course know, is the data structure that is the process descriptor or the task descriptor. And we have all kind of things there like the status, right? And like scheduling information and so on. Now, some of the things that we have is related to memory management, right? And some of the things that we have is related to like the process ID, group ID, and so on. But we also have descriptors for files of the user space, of the user, okay, of the process. So let's very quickly have a look at what we have. We have struct fs struct, and we have files, okay? So let's have a look at it. fs struct has a D entry for the root and the current working directory, and it has VFS mount pointers. So let's look for it. That's this guy, okay? And it has file struct, that is file. So fs struct has struct path for the root and the PWD of the current process. This is how we know like what is, you know, what is the get the current working directory, what is the root, and so on. And file struct is going to have here file descriptor table, okay? So we're going to have a file descriptor table, and we're going to have an FD array, which is the list of the currently open files, and we already covered the struct file, right? So this is the first part. I, of course, did not have time to do everything. Just for a quick recap, the idea is, and we're going to proceed it in the next lecture or recording, whatever you prefer, And to prepare, Linux prepares like the ground to populate in the first file systems. There are data structures that include setting up caches and enabling the VFS data structures. And Init is going to be put on the root file system once we actually go ahead and put it over there, okay? So this is going to be the end of this part. We're going to proceed with some examples later on, okay? So just if somebody has like any questions, I would be happy to take them. And I would be also happy to show you, just a quick run of it. Okay, so I was supposed to have it somewhere. Does anybody have any question or request like for the next time? Let's have a quick look. Okay. So, just to do like a recap and why it's colored and stuff like that, like, okay, I actually think it's the wrong one because this definitely is the wrong one because I put it in FS. Never mind. I'll do it like I'll do it on another time when I proceed like to talk. So, any question or any request for the next time? Because this is just part one, and the best is like ahead of us. All right. The best is of course Vadim talks. Okay. So I'm going to stop the first subject now. And happy to hear from you, and of course happy to receive more talks from you like over the CFP, okay? So that there will be more talks. And Vadim, would you like to take like a couple of minutes of break or start right away?
I think we'll take a 2 minutes break to people to absorb all the great talk, and I will start.
All right.
Like 9:50.
All right. So that's what we're going to do. Okay. All right. So guys, any question, anything, want to talk about anything in the meantime? למישהו יש שאלות? מה קורה? שרדתם?
בסדר גמור, תודה. רק נחדד את השאלה שלי עוד פעם, כי לא בטוח שסגור על התשובה.
כן.
לגבי ה-continuous memory, למה אתה צריך שזה יהיה רציף? מה הבעיה עם פרגמנטציה בזיכרון? בסופו של דבר, אם אתה יודע לאן הצ'אנק הבא הולך.
הבעיה עם פרגמנטציה בזיכרון היא שאתה... אוקיי, אז באנגלית, בסדר? So, by the way, I'm happy if anybody else could also like jump in. You will always have like, feedback. You will always have better responses than what I have, okay? Because like, hopefully, I really hope so, right? So the problem with memory fragmentation is that you always have to defrag it. Why? Because sooner or later, you would want to allocate, we did not talk about memory allocation in the body system here, but you would want to allocate big chunks. And if you are unable to allocate big chunks that are contiguous, then according to your memory allocation policy, that is, if you can wait or you cannot wait, then either your performance will, of course, degrade, or your allocations would fail. And since there are many things that are going on in the kernel, you cannot guarantee a very large allocation once some allocation have started. So there are fragmenting algorithms, but the cache system is so important and so used that you don't play with it, okay? For the most important things, you allocate everything immediately, like in the beginning, and like that's it, okay?
Yes, thank you.
Sure, and I'm happy, you can also call me like offline or something like that, and I'd be very happy like to sit with you and discuss whatever in a more profound way. I'm very happy to. But I just have a personal request. before Vadim starts, I really want you guys to tell me, also in private, if you want me to continue with this in the next hour, because as you saw in one of the previous talks, I talked for like 3 hours on one of the concepts. It's very hard to select like the right balance that will not be just too introductory. My objective is that those of you who are interested could reproduce themselves. This is why I'm doing it like on virtual machine. This is why I'm doing it Linux. Okay. All right. So enough with me. Our next speaker is Vadim Grinshpan and is going to teach us about the Checkm8 bootrom exploit. So there you go, Vadim.
Thanks again, Ron. Welcome, everyone. As Ron mentioned, I will describe the Checkm8 bootrom exploit. I will start by saying that unlike Ron, I'm not an expert, I'm not a hacker, I'm not a security researcher, but our group does develop a security product. So we are very interested in any security issues, exploits, and stuff like that. But I don't have the profound knowledge. So feel free if someone asks questions and I don't know. Uh, so Ron or anyone else that does know, feel free to answer. Okay, so let's start. A few words about myself. I'm working at ARM, almost 10 years in the embedded world. Many don't know, but ARM has a site in Israel. We currently develop security IP products called the Crypto Cell and Crypto Island, which provides various security features such as hardware cryptographic accelerator. It means like if your phones need to do some kind of encryption or decryption or key generation, it can offload the work from the CPU to our device and get the answer back really quick, and the CPU can work on other stuff meanwhile. And also it provides secure boot service and the hardware root of trust. So it means we have encrypted keys which are encrypted in hardware, defended by various components, and it allows the device to be very, very secure. Currently, our main goal is to replace the known SIM card with the iSIM, which is integrated SIM, which is like I think 100 times smaller and cheaper. But it's a hard task because the big SIM card we all know has very strong security and very strong certification. And our goal is to reproduce the same certification with very small and cheap device. So that's about that. So the agenda is the brief description of the boot process in the iDevices and what is the DFU. Description of the Checkm8 boot exploit, its stages and limitations. Short description of the use after free security issue. What can we learn from the exploit for our code we all develop? Nothing exciting, just the same things we all know, we see them again here. And questions, again, I don't know if I know how to answer it, but we'll try. Let's start. So what is Checkm8? It's an unpatchable open source bootrom exploit, which is runs from the iPhone 4S, which is very, very old, to the almost latest iPhone X, and it runs on all iOS versions. Also for every iPhone or even tablet has this exploit. The latest iPhone, I think it's 11, they already fixed it. So, but on I think tens of millions or maybe hundreds of millions of phones and devices could be exploited with this with this exploit, and it raised a lot of headlines, and that's how I learned about it, and I decided to explore about it a little bit. And I also had a lecture internally in our group. I presented it. So I took up on Ron's invitation and decided to share it with you as well. So what is the required tools? One of the most sophisticated devices, all you need to break into it is a Raspberry Pi, a battery, and 2 cables. That's it. And the source for almost everything in this presentation is this security blog, which I read. It's much more detailed than what I present here, so feel free to read there and learn. So what happens in the iPhone or iDevice boot process? So when the device is turned on, the bootrom is executed first. Its main tasks are platform initialization, all the registers and the CPU initialization, stuff like that. Verification of the image and transfer of the control to the next stage. So it's like the first stage boot and the second stage boot. We have the bootrom and the iBoot. So the role of the bootrom is to pass the control, to verify the image and pass the control to the iBoot. It has the built-in key called the GID key for decrypting the image. And it also has a public Apple key for the cryptographic functionality. And if further booting isn't possible, something broke, there is a DFU, device firmware update, which we'll talk about.
And I have a question.
Okay.
It might be unrelated to the lecture itself, but I was always wondering how the keys, how the firmware can be authenticated with the keys, because if they are stored in the hardware itself, the private keys, the hacker the hacker that modifies the firmware can also modify them, or they are literally burned inside the hardware.
I think in this case they are burned inside the hardware. And each device should have a unique ID and unique key also.
Okay, thanks. So basically, only when you buy a new computer, you can. No, I think I answered myself. Okay, thanks.
No problem. So the bootrom code is usually very, very, very small, because we don't, as someone that writes boot by himself, we don't want bugs in the boot, because it cannot be updated. Okay, it's stored in the read-only memory when the device is manufactured. It's not like a firmware update that can be done if we have a bug in the runtime code. The boot code is critical. It means that errata must be sent to customers, and it's also the hardware root of trust for all the chain. So as you see in the image, if this is compromised, the whole chain is broken. I can do whatever I like, but it's usually also very hard to do it. Okay, because the bootrom, again, it's very secure, very small code. It doesn't supposed to have bugs, and especially such big bugs that like described here. So what is DFU? Like you saw in the picture previously, the way to activate this exploit is through the USB cable, okay? And it allows the device, if something is broken, critically bad, and when the bootrom is something not okay there, it allows to restore the device through the DFU, device firmware upgrade. And it allows to send something called IBSS, which is iBoot single stage boot, which is a stripped down version of the iBoot. missing things such as Ron described with the file systems. So it doesn't have very complex systems. It's a simple version of the iBot. And again, DFU is also part of the secure ROM. It's burned into hardware and it can't be removed or updated. So again, if you have a bug there, you have a problem. So the exploit itself looks very simple. It's open source, Python code. Um, and we'll go through the basic steps here, what is done. So the first stage here is to prepare the data does eventually the exploit, that we send this data and the device becomes unusable or controlled by by the script, and it's the configuration and the data itself is dependent on the device. So the iPhone 4S is not the same, doesn't have the same data as the iPhone X. Okay, so here the attacker prepares all the needed data. Then we have something that the attacker calls heap feng shui. Okay, by the bug that is in the code, he rearranges the heap so it will be easily attacked. Okay, so this is this step. Each call for this function is just a USB. It's different types of messages, but it's basically just a USB message with some data, and I will show it later. And after that is the heap occupation itself. After we arrange the heap as we would like, we control. This line sends the data that after this is sent to the device becomes spawned, becomes exploited. And after this, we just put the data, the image that we would like to put. We can put almost anything here, any image, any data, all the payload, and the device will be booted later with anything we'd like. Looks very simple. We will not go into all the details, okay, because it's quite complicated, and I'm not also an expert on the USB protocol exactly and how they do it exactly, but the principle is pretty clear and pretty simple. So I will only describe the basic principle. So we talked about the stages. It's the heap feng shui, the allocation of freeing an IO buffer without clearing the global state. I will talk about it also. And the overwriting of the USB device IO request. This is the message I showed you here. This is the overwriting of the heap. And it's done with use after free, which I'll also describe. Use after free is a general term for a known security issue that's very common. These steps, I won't describe them in detail. They're also less interesting because this is the real bug. This is only technical how to control it later. So we'll start with the heap feng shui. Okay, what does it mean? Okay, so as I told you earlier, there are three functions here: stall, leak, and no leak, which are basically USB messages for different types, and they differ by if they're asynchronous or synchronous, and they differ by the last parameter, the timeout. Okay, because with this parameter of the timeout, the attacker tries to achieve something that also I'll describe later. So this here you see all the parameters this function gets. What is important here is the type of the request, the data and the timeout. We'll see what's the problem soon enough. So for any of the messages, libUSB messages, there are 30 bytes allocated in the heap for an object of the following structure. Okay, this is part of the DFU code. Each message gets this type of IO request structure, which is allocated, and this is how the DFU code handles the request. And the most interesting fields here are the callback and next, because the attacker goal is to control this. And if we control the callback and the next, we can call whatever we'd like. And this is what actually happens. We'll see it soon. So for a standard request, and all the requests here are standard, there is a standard callback that looks like this. Okay. Just to clarify, as you see here, all the code snips are from the reverse engineering done by the researchers, and not the actual boot code, because it's secret. But the code was already leaked in the past, so a real hacker will have access to the code. The code itself is not a secret, although everything in the iPhone is a secret, as you know. But all the code, it's not a real code from the boot, it's from the reverse engineering done. So there is standard callback for each request. And if the condition is satisfied, this condition, it's not really important what it means. But what is important that for each request that satisfies this condition, there is a call to a function called the USB core send ZLP. ZLP is a zero length packet, and this request is added to the execution queue because it needs to be sent back to the caller, to the sender of the request. This is part of the USB protocol transaction. Okay. So the attacker's goal is to control when this is called and when this is not called. Why? We'll see. So by selectively calling the USB core send zero length packet, when going through the execution queue and freeing the request afterwards, we can gain sufficient control over the heap and then exploit use after free. So how does the cleanup look? The cleanup loop, when we are done handling all the requests or we are doing a reset, there is a cleanup loop while aborted list, while we still have messages in the list. We clean up, we call another function called USB core completion endpoint. This is a mistake. It should be completion endpoint IO. But this call itself, it also calls the zero length packet. And what happens? The cleanup loop, basically the cleanup loop is okay. But what happens that the zero length packets are remain in the heap. So after a few iterations like that, there are still zero length packet allocated, but here a free space is gained because the cleanup is done for all the regular messages, but the ZLP are left here. So if you control the ZLP and how many are there, we can know what's the status of the heap. So this is bug number one. Here we see few bugs. What is interesting about this exploit that we see few bugs that looks by the look of it unrelated, but when they connect them together, they were able to easily break into the very secure device like the iPhone. So this is very interesting here because this is the bug number one. Okay, the zero length packet remain allocated, and it affects how the heap looks. Okay. So how does the heap usually look? The heap of the DFU code. Okay, so we have some string descriptors, the nodes, manufacturer. It's not really important. The task structure, the task stack, the IO buffer, which is all the requests and messages end up here. Some configuration field, half speed and full speed, and the room for the messages and the zero length packets. So by what we showed earlier, by this loop, okay, and by the leftovers that left in the heap, they were able to move the fields as they wish, as it's convenient to the attacker. We can see simple demonstration. Just a minute. If we look in the code itself, not in the code itself, by the blog I talked to you about earlier, from here it's simple to see because here they simulated. It's not, of course, it's not the real code of the DFU, but they simulated the memory allocation and the memory movements that were here. So here you see all these fields we talked about here. They malloc them as it's in the real DFU. They malloc the task, the task stack, the IO buffer, the fields of the configuration, the half speed, full speed, and the zero length packets, which are called zero length, but they are actually 30 bytes, okay, because it's every packet has a size. So what they did there, as in the exploit code, they sent two zero length packets, which are malloced. The IO request is freed, but the zero length packets are not freed because this is the bug in the DFU. So they printed how the memory looks before these allocations and after this allocation, and they ran the loop as the real exploit code sends the USB messages, and they did it again as a simulation to the real code, and they saw that the offset of the IO request was 5C0 in hexa. The HS offset was 4C0 in hexa, and the FS offset was 540 in hexa. And because they have this information, they know how to prepare the data for the exploit, because this is the actually data descent, which is, you see, the 5C0 is like this offset, okay? Because we know how the heap looks, the attacker was able to exploit it and send the code of the actual exploitation. Any questions so far?
Yes, so the vulnerability here is the use after free of the zero length packet. You can control it basically, and then you know the length of the freed heap between the two bounds, which are the zero length packet.
Actually, until now we didn't see the use after free. The use after free, until now we saw just the leakage of the memory, which we gained the attacker the control of how the heap looks. Until now we don't have use after free. We'll see it later. This is the second stage. the first stage is to arrange the first stage is to arrange the heap. The second stage is the use of the use after free. We'll see it very soon. Okay, so at this stage, an incomplete out request in DFU and in the DFU code, there are in request and out request. So the part of the DFU code is to create the out request for uploading the image. Out request for uploading the image is created. Okay, the DFU is ready to receive the new image. Okay, because again, the goal of the DFU is to restore the device with the new image that will enable the device to boot. At the same time, a global state is initialized. Also, it's part of the DFU code. And the address of the buffer in the heap is written to the IO buffer. And after that, the DFU reset with the clear status request, and another iteration begins. Okay. Again, this was all controlled by the USB messages of the attacker. Because the DFU code thinks it's a valid image that is sent. Okay, so what happens now? Now is the actual use after free, which will, again, we will soon describe it in more detail, but here it's in short. This struct, we already described it. Each IO request gets this type of struct, and it's allocated. But in this case, it's overflown with this message, whose content was defined at the first stage. This is the struct that we prepared with the offsets of the data and all the knowledge of the heap we already know. And those values overflow the fields of the callback of the next. And after that, the device is really broken, okay? And what is important here, the type of the request, type of the message is set configuration, which is supposed to update specific fields called half speed configuration, full speed configuration. And what happens is the code thinks we're writing here, but the code thinks we're writing here, but in fact we're writing in other place. Okay, this is what allows to overflow the callback and next. So why does use after free occur here? And I know it's a lot of words, but bear with me, it's pretty simple. Okay, when USB is started to get an image over DFU, the DFU registers an interface to handle all commands and allocates a buffer for input and output. Okay, that's the beginning of the world. There's a location of buffer for input and output. The interface code verifies that the W length, the length of the request, of the IO request that is sent, is shorter than the input-output buffer length. So we'll have enough room to store the message. And if that's the case, it updates a pointer, which is passed as an argument with the pointer to the input out of the buffer. The USB main code then updates a global variable with the length and gets ready to receive the data packages. Okay, now the USB code, the DFU code, ready to receive the new image. If the data package is received, it gets written to the input-output buffer via the pointer, which was passed as an argument. If all the data was received, the DFU specific code is called again, and then goes to copy the contents of the input-output buffer to the memory location from where the image is later booted. When the image is done, we copy it to another place in memory, and then in the next iteration, the boot happens from this memory. It's not we don't do boot from the local input-output buffer. After that, the USB code resets all variables and goes on to handle new packages. If the DFU exits the input-output buffer is freed, and if parsing of the image fails, the bootrom re-enters DFU. Okay, so if the image is not good, not verified, broken, we go to another iteration. So what's the problem here? At step 3, the global variables are updated and the bootrom gets ready to receive the data. Okay, like we mentioned here, there are global variables and they update with the length and ready. Then, if USB reset is triggered, then the image parsing will start. If that parsing fails, the bootrom will enter DFU once again, but step 6 wasn't executed. So the reset didn't occur because the reset and the clearing of all the variable didn't happen. And if we do a reset immediately after the global variable initialization, it means that the global variable will remain set. So step 6 of the clearing wasn't executed, so the global variable will still contain the same values. However, step 7 was executed. It means that the input-output buffer is freed. So because of that, we have a buffer that is freed, but the global variable, okay, that is set in step 2 is still set. It still points to it. Okay, classic use after free. Because of that, it's easily possible to trigger a write to an already freed buffer by sending data to the device. So it's the bug number 2. Okay, we have the first bug that the zero length packet remained in the heap. Bug number 2, which again looks unrelated. Okay, they are missing clearing. What was supposed to happen here? That if the code reset or exits, we need to clear also the global variable, but it wasn't done here. So apparently unrelated bug number 2, but when the attacker connect them together, it allowed them to control the device, get the access and use the exploit. And after that, it's the technical part, the easy part, the loop of length of the payload of the image, whatever the attacker wants to put on the device, on the memory. But it does need to be of specific structure because the next steps need to this payload needs to look like a real valid legit boot image. Okay, so there are fake translation table, fake descriptors, disabling of some configuration of the CPU, and callback chain. But this is purely technical. Okay, just need to look like a duck. Okay. So what are the Checkm8 limitation? It can't be executed remotely. Someone must take physical possession of your iPhone, iPad, or other iOS device, physically connect the USB cable, and physically run the Python script. Okay, it isn't persistent. It can be used to run unsigned code on your device, but the code only lasts until the device is rebooted. Then it goes right back to the normal, and you'd have to go through the whole exploit process again to run the unsigned code again. And it doesn't compromise the secure enclave on the A7 or later. It can't beat the hardware encryption, getter untouched ID, or passcode. So basically, the secrets that are stored in the iPhone, the attacker can't steal them. He can boot whatever he like, but he can't get access to the safe. So the secure enclave, it's like a safe inside the iPhone, which holds the keys and very secret things. It's similar to what we in ARM Israel work on, the crypto island. It's like an isolated safe which holds secrets. So this is why it's not that bad. This is what, because if it could be run remotely, then we could throw away all the iPhones in the world. But because it needs physical connection and because it's not persistent, it's not that bad. Okay. So what can we learn? Why did I do this talk in my group and why did I do this talk now? Again, stuff we already know, but just to remember again, okay? If you write boot code or actually any code, but especially boot code, we need to be very careful with the dynamic memory. See, we have zero leakage, okay? Same regarding usage of global parameters in the boot. In our code, each exit from the code clears everything. There's nothing left, okay? No data, no parameters, nothing. Few minor bugs used together, one huge boot exploit. So we can say this bug is minor, it's not critical, but when we have a minor bug plus another minor bug, it can create very serious issue. And if your code is in high profile like the iPhone, every little bug will be probably found and exploited, so be careful. That's it. It's a little bit lighter, I think, than and not that profound and deep like Ron talk, but I think it gave general good idea of what it is, how it's used. If anyone has any question, I'll be happy to answer. Anyone alive?
Yeah, I'm alive.
Okay,
Oh, that was a good talk. Thank you.
great, thanks.
It was an excellent talk. Yeah.
Okay, that's it from me. Thank you.
Thanks a lot.
Okay, thanks, Vadim.
If you're interested, I can do. I have also idea for security issues talk, or things that I'm more familiar with than what I talk about now. If you'd like, side channel attacks and secure coding, how can we protect from it? Tell Ron or write in the group what if it can be interesting for you.
Yeah, that would be great. So I think we're just people from Israel now, so we can go back to Hebrew. Am I wrong about it? No, I'm not wrong. So, all right. So hold on one sec.